Billions of years ago, Earth didn't exist. No oceans, no mountains, no life. Just a giant cloud of dust and gas floating in space. Fast forward to today, and here we are, living on a planet that seems tailor-made for us. But how did this happen? How did a lifeless cloud turn into the vibrant, life-filled Earth we call home? And here's the kicker. Where did all the water, the very essence of life, come from? In 2005, NASA sent a probe to a comet to find answers, and what it discovered will blow your mind. Stick around, because this story is wilder than fiction. However, 5 billion years ago, Earth did not exist at all. The location where Earth and our solar system are today is at the edge of the Milky Way galaxy. Before our planet formed, there used to be a massive cloud in its place. This cloud was filled with dust and gases. What exactly happened to this cloud that transformed it into a planet, the very planet we live on today? This cloud of dust and gases is called a molecular cloud. It contained dust particles, including sand, silicon, and various metal elements. The birth of this cloud was caused by different dead stars. In the early universe, stars that had burned all their fuel exploded, scattering their remnants across the cosmos. Unlike the clouds we see in the sky, these molecular clouds look different. They have been captured using the Hubble Space Telescope. Astonishingly, this cloud was as large as 100 light years across. That means if light traveled from one end to the other, it would take 100 years to cross. To put it simply, this dust cloud was 6 million times bigger than the distance between the Sun and Earth. This was the very cloud from which new stars and planets formed. The force responsible for the formation of stars and planets within this cloud was gravity. Yes, gravity, the same force that exists in space, but is generated due to the presence of mass. Objects in space attract each other due to their gravitational pull. The more massive an object is, the stronger its gravity. The particles in the molecular cloud began sticking together due to gravity. Larger particles started attracting smaller ones, causing them to collide rapidly. This generated energy, which heated the rotating core of the cloud. Over millions of years, this process continued, and the molecular cloud's core grew larger, spun faster, and became hotter. Eventually, this core turned into a massive fireball, our sun. The remaining molecular cloud began orbiting the sun. The particles and gases within it later formed the planets, including those that sustain life, and the moons orbiting those planets. But how exactly did this happen? In the 1700s, German philosopher Immanuel Kant and French scholar Pierre-Simon Laplace proposed the first hypothesis about the formation of the sun from a molecular cloud. However, at that time, it was just an idea. Between 1920 and 1950, advancements in telescopes made astronomical observations more precise. Yet, even then, it was impossible to see inside these clouds. The problem was finally solved in the 1970s and 1980s with the invention of radio and infrared telescopes. These telescopes allowed scientists to peer inside dust clouds and observe stars forming within them. This confirmed that new stars are born inside molecular clouds, and that the remaining dust particles eventually form planets. But how does this process begin? Many theories were proposed. Then, in March 2003, an experiment aboard the International Space Station provided a long-sought answer. Astronaut Don Pettit conducted various experiments in microgravity to see how different substances behaved in space. He created water bubbles, dissolved rings inside them, and placed salt in a plastic bag, spinning it. Though his primary goal was different, his final experiment answered an age-old question. When salt was placed in the plastic bag, its particles began sticking together over time. This demonstrated that in space, particles attract each other. Scientists believe that in the molecular cloud, tiny and large particles, all orbiting the sun in the same direction, started clumping together in the same way as the salt particles in Pettit's experiment. This marked the beginning of planet formation. Around 4.5 billion years ago, within the molecular cloud, these particles formed clusters, just as Don Pettit's experiment showed. When these clusters reached a size of about 1 kilometer, similar to a mountain, their gravity increased significantly. They started pulling in nearby particles, just like a vacuum cleaner sucks in dust. For the next 3 million years, this process continued. Eventually, 20 planets emerged, all orbiting the sun. Because these 20 planets had grown significantly, their gravity caused them to attract each other, leading to collisions. Each collision merged 2 planets into a larger one. Over time, these collisions reduced the number of planets from 20 to just a few: Mercury, Venus, Mars, and our Earth. However, at this stage, Earth was not the blue, life-filled planet we know today. Instead, it was a fiery mass due to these violent collisions. If an organic molecule had formed at that time, it would have vaporized instantly. Life could only emerge once Earth's temperature dropped. But before that, Earth had to survive one of its greatest threats: solar storms. Yes, the intense radiation from the sun's storms can severely damage a planet's atmosphere. These solar storms have made life impossible on many planets, including Mars. So how did Earth withstand solar storms? The answer lies in its core. When Earth was forming, its temperature became extremely high, turning it into a fireball. Rocks melted, releasing iron and nickel. Due to their high density, these metals sank to Earth's core. Geophysicists believe that when molten iron spins, it generates a magnetic field. Since Earth's core contains large amounts of molten iron, it produced a strong magnetic field known as the magnetosphere. This magnetosphere extends about 370,000 kilometers on the sun-facing side, roughly the distance to the moon, and much farther on the opposite side. This magnetic shield protects Earth from harmful solar radiation. The weaker magnetic field at the north and south poles allows some radiation to enter, creating auroras, also known as the northern and southern lights. However, these radiation levels are too low to be harmful. Earth had survived solar storms, but it was still not suitable for life. It had yet to face another major challenge: a planetary collision. How do we know about this collision? For that, we must go back to 1960, when NASA sent astronauts to the moon during the Apollo missions. Initially, it was believed that the moon was a fragment of Earth that had broken away. However, lunar rock samples brought back by astronauts differed from Earth's rocks. These moon rocks appeared burned. Further investigation revealed that the oxygen isotopes in both moon and Earth rocks were identical, proving that the moon was originally part of Earth. The only event capable of causing such intense heat was a planetary collision. A Mars-sized planet named Theia collided with Earth while it was still cooling. This impact released enormous energy, scattering molten debris into space. Over thousands of years, these debris pieces clumped together, just like in the molecular cloud, eventually forming the moon. This collision tilted Earth's axis by 23.5 degrees, leading to seasonal variations. Without this tilt, Earth would not experience changing seasons. Seasons influence food production, rainfall, and oceanic tides, which distribute nutrients essential for marine life. But the biggest mystery remained: where did Earth's water come from? In January 2005, NASA launched the Deep Impact Probe to investigate a comet named Tempel 1. It discovered frozen water within the comet, confirming that comets contained water. Scientists believe Jupiter's immense gravity altered comet orbits, causing them to crash into Earth, delivering water billions of years ago. Thus, Earth became a habitable planet. Now, let's dive deeper into some fascinating details about Earth's formation. Did you know that the process of planet formation is not unique to our solar system? Astronomers have observed similar processes in other star systems. For instance, the star system HL Tauri, located about 450 light-years from Earth, has a protoplanetary disk where planets are forming right now. This disk is filled with dust and gas, much like the molecular cloud that gave birth to our solar system. Observations of HL Tauri have provided valuable insights into how planets form and evolve. Another interesting fact is that the Earth's core is still cooling. The heat from the core drives plate tectonics, which is the movement of Earth's crust. This movement is responsible for earthquakes, volcanic eruptions, and the creation of mountains. Without plate tectonics, Earth's surface would be flat and featureless, and life as we know it might not exist. The cooling of the core also generates Earth's magnetic field, which, as we've discussed, protects us from harmful solar radiation. Speaking of the magnetic field, did you know that it's not constant? The Earth's magnetic poles have flipped multiple times throughout history. The last reversal occurred about 780,000 years ago. During a reversal, the magnetic field weakens, leaving Earth more vulnerable to solar radiation. However, these reversals take thousands of years to complete, so we don't need to worry about it happening anytime soon. Let's talk about water again. Water is essential for life, and its presence on Earth is one of the key factors that make our planet habitable. But did you know that water is also found in other parts of the solar system? For example, Europa, one of Jupiter's moons, has a subsurface ocean that might contain more water than all of Earth's oceans combined. Scientists believe that Europa's ocean could potentially harbor life, making it a prime target for future exploration. Another intriguing fact is that Earth's atmosphere has changed dramatically over time. The early atmosphere was composed mainly of carbon dioxide, methane, and ammonia, with very little oxygen. It was only after the emergence of photosynthetic organisms, like cyanobacteria, that oxygen levels began to rise. This event, known as the Great Oxygenation Event, occurred about 2.4 billion years ago and paved the way for the evolution to complex life forms. The Earth's atmosphere also plays a crucial role in regulating temperature. The greenhouse effect, caused by gases like carbon dioxide and methane, traps heat and keeps our planet warm. Without the greenhouse effect, Earth's average temperature would be about -18 degrees Celsius, making it too cold for most forms of life. However, human activities have increased the concentration of greenhouse gases, leading to global warming and climate change. Let's not forget about the role of the moon in stabilizing Earth's rotation. The moon's gravitational pull creates tides, which have shaped coastlines and influenced the evolution of marine life. The moon also helps stabilize Earth's axial tilt, preventing extreme climate variations. Without the moon, Earth's tilt could vary wildly, leading to unpredictable and potentially catastrophic climate changes. Finally, let's consider the future of Earth. Our planet has undergone numerous changes over billions of years, and it will continue to evolve. Plate tectonics will reshape continents, volcanic activity will create new landforms, and the climate will change in response to natural and human-induced factors. However, one thing is certain. Earth will remain our home for the foreseeable future, and it's up to us to protect and preserve it for future generations. Earth's journey from a dusty cloud to a life-filled paradise is nothing short of miraculous. Let's cherish and protect this incredible home we call Earth. Stay curious,